Hey guys, Dr. Bitz here coming out with another fantastic video, and today we're talking about lipids. Lipids, those insoluble things that we all love. The oil you put in your pan, the butter you put in your pan, the cholesterol that clogs your arteries. These are all lipids. And today we're going to learn a lot about their reactivity, what they can do, and we're going to make a little bit of soap. Hey guys, we're still in coronavirus shutdown mode, but here we are in the lab trying to get it done for you guys, trying to get everything we can up online before they completely close us down. Hopefully they never will. Hopefully we'll have lots of time to film more video for you all. But we're doing our absolute best. We would appreciate your patience and your kind words as we move forward through this together. We are going to get it done, guys. So a little more talking. Let's get after it. Let's get it done. All right, guys. We'll be starting with part 1, identifying lipids from a molecular model. Here we have a fatty acid. Right here we have a carbon. The black balls are carbon. The red balls are oxygen. The white ones are hydrogen. Carbon, double bonded to an oxygen, so it's a carbonyl. I don't know if you can see the double bond on the camera. Let me pick it up and kind of show it to you. There you go. They're double bond to the carbon. So this is your carbonyl to an OH. So this is an example right here of a carboxylic acid. So this is the acid part of the fatty acid. Going this way along the molecule, you'll see there's a whole bunch of black balls. These are carbons. This is your lipid part, or your fat part, or your non-polar part, the part that doesn't like water, right here. Now, there should be a lot of hydrogens on these carbons, but we don't have them on there for simplicity's sake. We're just trying to make the model easier to look at. If we put the hydrogens in, it gets really messy really fast, and I'll show you an example of that when we look at a wax. Okay? So this is a fatty acid. Moving right along. Here we have a steroid. Now, steroids are a lot more complicated than fatty acids to look at, but they're really kind of cool. This is a steroid nucleus. All steroids share this same structural pattern. Here we have a 6-membered ring, 1, 2, 3, 4, 5, 6. Another 6-membered ring, 1, 2, 3, 4, 5, 6. Another 6-membered ring here, 1, 2, 3, 4, 5, 6. And a 5-membered ring right here, 1, 2, 3, 4, 5. So we have a 6, 6, 6, 5 ring system. One more time. 6, 6, 6, 5 ring system. All steroids share the same ring system. They all have that 6, 6, 6, 5 ring system. If it doesn't have a 6, 6, 6, 5 ring system, it is not a steroid. It is some other kind of molecule. Okay? That's a steroid. Next, a triacylglycerol, probably the more complicated of all of them. Let me see if I can get this model done for us. It's really messy and it's really hard to see even in person. So on the video it's going to be very challenging. But we're going to do our best, right guys? We're all in this together. There it is. This thing is hard to look at, guys, and I feel like I need to apologize, but I can't because this is all I can do right now. So here we have a carbonyl. Here we have another carbonyl and another carbonyl. So we have 3 carbonyls. 1, 2, 3, okay? Each one of these carbonyls has a long chain, a fatty acid or a fatty tail on it right here. I know it's hard to see, guys, but there it is. Carbonyl, 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 long carbon chain, long carbon chain, long carbon chain. And they're all attached to a molecule called glycerol. Well, that's not as important right now. So I want to kind of drive home to you how complicated these molecules can get. Even though this isn't really a very big triacylglycerol, they're just very complicated molecules. And this is one of the ways your body will store fat. And it's actually kind of a cool process. So there's a triacylglycerol. Do your best with that, guys. I understand that it's really hard to see. There's a drawing in your manual, so you can kind of look at the drawing there. Again, I get it, guys. Hard to see. Do your best, okay? And finally, a wax. Now, a wax is also quite complicated, but not nearly as complicated as a triacylglycerol. So now, let me get these models out of the way. There we go. So now this wax has a carbonyl, and attached to that carbonyl, let me just flip that over. Attached to that carbonyl is an oxygen. So this is an ester bond, okay? This is an ester. It looks like a carboxylic acid, but it's not. It's an ester. Carboxylic acid would have a hydrogen here. This has a carbon-based group, okay? So a wax has an ester. And on one side of the ester, there's a long chain of carbons. And on the other side of the ester, there's a long chain of carbons. This is called a wax. These are pretty easy to identify. Everyone kind of remembers these because they're so easy to identify. An ester, Long carbon chain to the left, long carbon chain to the right, wax. All right, guys? And that is the end of part 1. So we'll move on now to part 2. See you soon. All right, guys, here we go. We're going to do part 2 now of the lipid experiment, cis versus trans fatty acids. Now, as you can see in this video, we have cis fats and trans fats located right here on our desk. Now, these are molecular models, so we can look at them closely, examine them closely, and try to figure out what the differences between a trans fat and a cis fatty acid are. And it's very simple. It's a double bond. Cis and trans fatty acids have double bonds. Now, as you can see here, this double bond, there's a hydrogen going that way, and another hydrogen here coming towards me. This is a trans orientation of the double bond. This one here, as you can see, the double bond is right here. In case you can't see it, there's a double bond. Okay. This hydrogen is pointing towards me. This hydrogen is pointing towards me. This is a cis orientation of a double bond. So this is a cis fatty acid, and this is a trans fatty acid. And all it is, all cis and trans means, is the orientation of the hydrogens on the double bond. This is trans because one's facing one direction. The other hydrogen on the double bond is facing the exact opposite direction. Cis means that the two hydrogens that are part of the double bond, here and here, here's the double bond, these two hydrogens are facing the same direction. That's what cis and trans means. And these are cis and trans fatty acids. All right, guys? With that, I want to move on to experiment number 3. Here we go. All right, guys. Now we're going to weigh out 2.5 grams of this vegetable shortening, Crisco. You can buy that at any store here in Florida. So now I'm going to weigh directly into this Erlenmeyer flask because Crisco is really, really messy to work with. You're better off weighing directly into the flask. I'm going to re-zero it. There we go. 2.5 grams. Doesn't take very much, believe it or not. Better to go under than over, really. Let's try to get this in the bottom here. See how it kind of just smears around? 2.4. That's good enough. I'm not even going to go for more. 2.5 is what we wanted. 2.4 is what we get. I'm very happy with that. So now, we're going to move on to the next step. All right, guys, now that we have the fat in our flask, you can see the nice Crisco right there. We're going to put this little white bar into it. Now, this, see if I can get it on the camera. There we go. This white bar is a Teflon-coated magnet. And we have a stirring hot plate that has a magnet underneath of it on a motor that spins, causing the magnet to spin in this little Teflon coat, causing it to stir my reaction. So I don't have to stand there with a stirring bar or a glass rod or whatever and go tink, 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 tink. I just add this. Watch how cool this is. As you can see, the stirring bar is trying to move. Now the Crisco will, because it's not dissolved yet, it's not being dissolved and heated yet. The Crisco is very sticky, so the stir bar has a hard time moving. But once we start heating it and have everything added to it, it'll start moving quite freely. So now I'm going to add the sodium hydroxide, and I'm going to add the alcohol, the ethanol. All right, guys? Be back with you in a minute. Okay, guys, we're back again. Now we're going to do the adding of the liquid material, the sodium hydroxide and the ethanol. Now the sodium hydroxide is going to be your chemical that does the reaction. It's going to take the lipid, the fat, and it's going to break it down into the soap particles or the soap molecules as well as the little bit of glycerin. So here comes the base that I'm pouring in right now. There we go, 5 milliliters. Now here comes the ethanol, 5 milliliters. This is going to act as a more or less a transfer catalyst because, you know, fat and water don't want to mix real well, so we give them something to help them along a little bit. There we go. And let's get this thing stirring. There we go. Let's get the heat turned on. Bear with me here. There we go. Let's crank it up a little bit. Let me double check my volumes, make sure I added enough. Oh, we're supposed to add 10 mils, guys. I'm sorry. Let me add a little bit more of each one. Supposed to add 10, not 5. I added 5 each. So I'm just going to add some more. No big deal. There we go. There's 5 more mils of ethanol. And we'll do 5 more mils of the sodium hydroxide. So always pays to double check. We're all human. We all make little mistakes here and there. This is a very easy one to fix. There we go. Poured it down the sides. And now we let it stir. And we just kind of wait for it to do its thing. It says in the book we want to turn the hot plate up to 100, so we'll give it a little more juice. What temperature do we want? The book says we want to be at 80, right around 80 degrees. So let's put a thermometer in there. We can track the temperature. Let's crank that up to 100 just so we can have good heating. Let's get the stirring going a little quicker. There we go. Now, we're going to let that stir. I'm going to do something a little fancy. I'm going to go grab what's called a hot air gun. So I can get the soap down into the flask a little faster. Normally we wouldn't do this. We would just let the heating do it. But why not, right? Why not get a little fancy and move forward in life? All right, guys. We're going to let that go. See you soon. All right, guys, as you can see, the solution is starting to get opaque. We heated it up, we hit the 90-degree mark, and now we're just waiting for the soap to precipitate in the flask. And you can kind of see it on top. The little whiteness is starting to form on top. I feel pretty good that we're going to have some nice soap here in a few minutes. Let me just give that a swirl. See, you can see it there. You can see all that nice soap forming there. We're just going to give that a few minutes to cool down some more and try to maximize our yield of soap. Stay tuned. All right, guys, we've waited about 15 minutes, and as you can see, our flask is now filled with soap. Isn't that kind of cool, right? That is soap floating right there in solution, or in suspension, I should say. So now we are going to do what's called vacuum filtration. We have the setup here in the fume hood, and I'm going to just kind of zoom out here in a minute and show it to you. So let's just zoom back out. Don't mind me, please, with a little bit of disruption of the camera. There you go. Let me back up a little bit. There we go. Vacuum filtration setup right there. Now here we have what's called a Buchner funnel. This is a rubber stopper. This is a vacuum flask, and of course a clamp stand and a clamp. And this bad boy right here is a vacuum pump. It's going to pull the air out of here, which is going to pull the air through the funnel, which is going to help us filter our sample a whole lot faster. Of course, you need some filter paper. Make sure I'm on camera there. And so we're going to take one of these pieces of filter paper. You're supposed to use forceps for this. So let's just do that. There we go. Oops. Got to make pretty sure you just get one. Put it on top there. Close this box up. Now I'm going to take a little bit of water. This is just water. You remember these bottles from the lab, right? I'm going to squirt a little bit of water on here. And I'm going to turn the vacuum pump on. Oops, helps to plug these things in, Dr. Betts. Electricity, what a novel idea. And there we go. Now, we are pulling through the funnel. We're pulling air down through the funnel, and I'm going to pour on my sample. I got myself what's called a rubber policeman. It's used to scrape out the soap particles into the funnel. So I'm going to do that right now. There you go. I may not even need it. I'm going to rinse with a little bit of water. I'm going to use my rubber policeman to get in there and scrape off the sides a little bit. Pour it into there. Set that to the side. Now I'm going to wash my soap with a little bit of water just to rinse off any impurities that might be there. And that way our soap will be in good working condition. Of course, I'm not going to actually use it because you never use anything you make in a lab. Only use soap that you get from reputable sources, or if you make it yourself at home, that's up to you. But this is because I'm making it in laboratory equipment that I know has been used for other things. I wouldn't dare use this on my skin. It's just not safe. Alright, so now it's pulled pretty good. Let me see if I can get you guys a nice close-up of the soap that we created. So don't mind me, guys. The camera's going to move. Just bear with me, please. See if I can bring the soap a little closer, maybe? There we go. There we go. Let me zoom in on that for you. And there it is. Now, it doesn't look like bar soap because I didn't pour it into a mold or anything. If I really want to have nice barred soap, you could pour these things into molds and all that kind of stuff. Now, if I were to push on that soap, it would be very mushy. It's still made from fat, don't forget. So it's very mushy in texture. And that's soap right there. We made our own soap. Isn't that kind of cool? Now, the next step is I'm going to do a quick weight of it. It's going to be a wet weight, so the mass of the water is going to be included in the soap. The best thing to do if I really had time is I would wait a couple of weeks, let the soap dry, and then get the mass of the soap at that point. But there's really no need to do that. This lab still drives the point home. All right, guys, so let's go weigh it. Okay, so now it's time to weigh our soap. Just as always, I'm going to take a weighing boat, place it on top of the pan, and then re-zero. Now I'm going to use a spatula, a laboratory spatula, if I can find one. I can't find one. I'll just use a spoon. This is a laboratory spoon here, guys. And I'm just going to transfer my soap as best I can, as neatly as I can, onto the weighing boat. Try to get all of it as best I can without breaking the equipment. Spoons aren't the best thing for this, but it's what I had on hand. There we go. And a little bit in there. Let me see if I can get it onto the weighing boat. There we go. I got it. There, very good. All right, and I got 7.611 grams of soap. Now, don't forget, this is wet, so I'm weighing the mass of a lot of water too. All right, guys? So there's the mass of our soap.